Welcome back to the Mechanics of Solids lecture series. In this series of videos, we're evaluating deflections using the superposition method with the assistance of beam tables. In the previous video, we were working this example of a simply supported beam. We had already found V sub C, and in this video we'll continue by finding V sub D and theta sub A, starting with V sub D. Since the load cases are pretty much the same, I went ahead and laid it out for us. We can evaluate the deflection at D by superposing the following two cases. Case 1, the deflection at D due to the point load, which I'll call VD1, and case 2, the deflection at D due to the distributed load, which I'll call VD2. And the superposition method says that the total deflection at D, V sub D, is equal to VD1 plus VD2. So starting with case 1, the point load, this is very similar application to what we did in the previous video. If we look at the beam table, it's the point load somewhere not in the center of the beam, and we want to evaluate the deflection on the right of the load. The equation is for 0 less than or equal to x less than or equal to a, the left side of the load, so we have to flip it. So again, we're going to flip it and label this distance up to the point load B, the other distance A, and we'll use the same equation. I've already laid that equation out. This distance right here is equal to B, 3 feet. This distance here is equal to A, or 9 feet. The only thing that changes is the location that we're evaluating the deflection, which is x, and I'm going to label x the coordinate from the right end of the beam. So I want to evaluate it right here, and that distance x is equal to 4 feet in this case. To summarize, B equals 3 feet, x equals 4 feet, and the length of the beam is 12 feet. Okay? Plugging in the numbers, VD1 equals negative P, 20 kips, B 3 feet, x 4 feet, divided by 6, L 12 feet. Leave EI symbolic for now. Multiply by 12 squared minus 3 squared minus x 4 squared. Oh, that whole term is feet squared. It computes to 396.67, and the units are kip feet cubed. So we're going to multiply that by 12 cubed inches cubed to get to inches cubed, and then divide by EI, 1.2 times 10 to the 6th kip inches squared, and the whole answer reduces to, I should have a negative sign here, and a negative 0.571 inches is my answer for VD1. Case 2, the distributed load. Let's look at the load case. It's distributed load over part of the beam. Notice that we're wanting to evaluate the deflection right at the end of this distributed load. So that is a special case, this one right here, at x equals a, and we can use this equation. Of course, we have to remember our distributed load is at the right end of the beam, so we're going to flip the coordinate system once again. Coming back here, we want to define this distance, x equals a equals 4 feet. Okay, the equation for case 2, I'll go ahead and copy it down here. This came from the previous page. VD2 equals negative W a cubed over 24 LEI times 4L squared minus 7AL plus 3A squared. I'm going to use the numbers A equal to 4 feet and L equals 12 feet. Calculations would be VD2 equals W is negative 5 kips per feet, A cubed, or 4 feet cubed, divided by 24 times 12 feet, carry my EI, and then in the brackets I have 4 times 12 squared for the length, minus 7 times A is 4, L is 12, plus 3 times A squared, or 4 squared. This term has units of feet squared. The number computes to negative 320. And my units again, kip per feet squared times feet cubed. Kip feet times a feet squared there. It's once again kip feet cubed on the top. Multiply it by 12 cubed to get to inches cubed. Cubed there. Divide by EI, 1.2 E6 kip inches squared. And I get a number of negative 0.461 inches for VD2. So to summarize, putting it all together, the total deflection is going to be VD1 negative 0.571 inches plus VD2 negative 0.461 inches, which computes to VD of negative 1.032 inches. Okay? And if you recall, that's similar but a little bit smaller than the answer that we got for VC, which makes sense. Finally, solving for the rotation. Again, the rotation is the same two load cases superposed before, but we're evaluating rotation at A instead of deflection. I can summarize the superposition method as theta A equals theta A1 plus theta A2, and we need to evaluate the rotation due to those two load cases. Starting with case 1, let's look at it. The point load. Okay, it says theta 1 equal to negative PB L squared minus B squared over 6 LEI. Theta 2, which one should we use? Well, if we stick strictly with this, we can use theta A, theta 1 equal to PB times L squared minus B squared over 6 LEI. So let me do that. Theta 1 equals, and I'm just going to drop the sign because I can see which direction the rotation is going in here. So if theta equal to PB times L squared minus B squared over 6 LEI. I didn't need to switch the angles here. I can go ahead and use A is equal to 3 feet and B is equal to 9 feet. And notice that the equation uses B. This one's fairly simple to calculate. Remind ourselves that B is 9 feet, L is equal to 12 feet for use in that equation. P is 20 kips times 9 feet times 12 squared minus 9 squared feet squared divided by 6 times 12 feet over EI. This computes to 157.5. And the units are going to be, those 2 feet cancel, kip feet squared over EI. So I'm going to multiply times 12 squared inches squared to get to be consistent with my units for EI, which is, EI is 1.2 times 10 to the 6th kip inches squared. Okay, that's gone. Notice what happened here. The units on the top and the bottom cancel, and that's what we expect because the value for theta should be a rotation, unitless, or it actually is in radians. So this is 0.019 radians for theta 1. Next, let's evaluate the next case, load case 2. I want to evaluate theta A2. Let's look at it. It's this one right here. We're given an equation for theta 1 and theta 2. Now we do have to make an adjustment here because the load is on the left side of the beam, and for our case it's on the right side of the beam. So what we're actually going to do is flip it and use this equation for theta 2 and call A the distance from the right side of the beam to the end of the load. So let's go ahead and do that. Call this distance right here A, which would be 4 feet. And therefore, equation that we saw on the previous page for theta, this is theta A2. This is theta A1 up here. Equation for theta A2, I'm going to drop the sign, and it is WA squared over 24 LEI times 2L squared minus A squared. We're going to use A equal to 4 feet, L equals 12 feet. Okay, plugging that in, W, 5 kips per feet, times A squared, 4 feet squared, divided by 24, 12 feet. I think I've done this enough times. I'll go ahead and do the include the numbers now. 1.2 E6 kip inches squared, and in the brackets 2 times 12 squared minus 4 squared. This is feet squared, and so I'm going to multiply it by 12 squared to get to inches squared. All of these units here should cancel out. You can stop and check more carefully for yourself. The number that I get is 0.009 radians for theta A2. Okay, so you can see that a lot of this is figuring out how to apply and interpret the beam tables, and sometimes when you need to make switches or flips like we did in this particular case, it can get a little tricky. Anyway, we're almost done with this problem. The total rotation is the sum of theta A1, 0.019 radians, plus theta A2, 0.009 radians, and that sums to 0.028 radians. And that is the answer and the conclusion for this problem.